All right, so what we're going to look at today is the power rule for derivatives. So if you have run through and done several uh, different examples of using definition of derivative, you would have found a couple of truths to be true. For instance, if you did f of x is equal to x squared, you would have found that meant that f prime would have been 2x. That's a simple one. If you had done slightly more complex using polygons, you would have done g of x is equal to, say, x cubed minus 5x to the 7th, and then plus 3. Now, if you have done that derivative, you apply the power rule or the definition derivative to that, you would have found that g prime would have been 3x squared minus 35x to the 6th power, and then the 3 would have disappeared entirely. Now, the issue becomes doing the definition derivative to this stuff right here, to g, especially because of this power of 7, is not terribly difficult, but it's not necessarily the simplest thing to do either. It takes some time. So the power rule is actually a much quicker process for us to do here. And basically what the power rule does, and if you pay attention to what happened here, you had a coefficient of 1 right here. So we did 3 times 1, we got 3, subtract 1 from the exponent, you got 2. Did the same thing in the second part. 5 times 7 gave us 35. 7 minus 1 gave us the new exponent of 6. You said, well, what about this last one here? Well, this last one is pretty straightforward too. It's x to the 0 power. You just don't normally write that, x to the 0 power. So 0 times 3 gives us 0. So it's plus 0 and it's gone, right? So that's what the power rule is for derivatives. It means that if you start off with f of x being ax to the b power, it means that f prime is going to be a times b x to the b minus 1 power. That's a b right there, okay? And that's your basic power rule. Now that comes in really handy when you start dealing with other functions that are significantly more complex, but I'll keep it simple for this next example just to make sure that we're getting the hang of this. So if I said that h of x were 7x to the 5th power minus 18x squared plus 2, h prime, now you can go on your own and do this using the definition of derivative and prove it. I encourage you to do that on some of these just because it's good practice, but this would be 7 times 5, which would be 35 again, x to the 4th power, that's a 4th, not a 9, I don't know why I did that, and then minus 36x, and then plus 0, because that would be x to the 0 again, so 0 times 2 is 0. So normally we don't write that, and we don't normally write the plus 0 down here. And this makes sense too, because remember, the idea behind a derivative is it is the change in that piece. It's the rate of change. So it's how quickly the y's are changing with respect to the x's. So 2 is constant. How is 2 changing? It's not. So its change is 0. So that's why it disappears entirely for us. Now this becomes a lot more useful to us when we start dealing with alternate examples. So for instance, let's just say, and I'm moving on to a new screen, I'm going to reuse x. Let's say f of x is equal to the square root of x. Now that is one that we've already done before. We've worked on it, and we did that would be one that you would do definition of derivative before. But what I'm going to do is I'm going to rewrite this for a second so I can use the power rule, because this isn't a power. But if I write it as x to the 1/2, it is a power. So that means that f prime is equal to 1/2 x, and then minus 1 from 1/2 because this is negative 1/2. So if I wanted to rewrite this, I could rewrite this as negative 1 over 2 times the square root of x. Okay? And that is how we do almost all of these. Is we look for how can we rewrite this using an exponent. And that works for all roots and all polynomials. So let's just say, I'll give you another example, and we'll use g here. Let's say that g was the 3rd root of x. Well, that means that g prime is going to be x, well, maybe let's go back here a second. This is x to the 1/3 power, right? Oh, so that means the coefficient is 1/3, right? And then subtract 1 from 1/3 because it's negative 2/3. Now the thing is, this is perfectly acceptable in this form. You do not have to rewrite this. So this answer right here is fine. But if you want to get a better understanding of what we're doing here, we could rewrite this. 1/3, and then we'd have the 3rd root of x squared. That negative moves it into the bottom, right? And also, oh yeah, this one right here, that is actually positive on f as well. I don't know why I wrote a negative there. The negative exponent moved it to the bottom over here. The negative exponent moved it to the bottom over here, which actually gives us a whole nother different way that we could be dealing with these. Let's just say that we had h of x is equal to 1/x squared. We want that derivative. Well, using definition derivative, this is not trivial. It takes a little bit of time to work through it, but it is also not terribly difficult to do this if we're going to do it using the power rule. Because this is a positive exponent, I could rewrite this as to the -2 power, and then it matches. So then I could say, well, this is x to the -3 power, because I would have subtracted 1 from the exponent, but first I would have had to multiply by -2. So it's -2x to the -3rd power, which I could then write as -2/x cubed if I wanted to rewrite it that way. So remember, the power rule in its most basic is all you're really doing is you're saying, let's rewrite whatever this thing is using a power if I can. Now this doesn't work for sine and cosine, of course. It doesn't work for our trig functions, but it works for anything that has anything remotely resembling a power. And that is true about rational functions like the h here, and it's true about radical functions like f and g. Okay, so you can write all those as any sort of those that you'd want. Okay?